Okay. Last line আছে আমি কি actually পড়ি আছিল কি পড়িতো curl of magnetic field. This is what we are calculating. So Biot-Savart law, curl right? এইটো আমাৰ whole Biot-Savart law পড়া যেটো magnetic field আছে for a current. Okay. Then we expanded this. Using curl of A cross B formula, and we found in the end, after lots of things, there were terms like mu naught over 4 pi, this just inside this thing. So we found that J R prime 4 pi 3-dimensional delta over R, right? It was a term asil. And then there was a term like del dot J, I think, or J dot del. What was the last line? J dot del prime. J dot del. So J of R prime dot del M R over R square. And this was the del. That means del del x, x cap, y, and this thing. We then switched del into del prime, which means del del x prime, del del y prime. And that brings a minus sign. Long discussions in the last class. That brings a minus sign. So basically, we can write this as, and we did that so that we can write this as del dot prime over, let's do piece by piece. So this I can write as R over R cube, right? Unit vector. And that we can break into x minus x prime, just x component, then again the same thing, y minus y prime over R cube, y component, and so on, right? You can do that because this is R over R square, R over R cube. And just one piece, if we can show that this is 0, others will be 0. You will understand why. So, kyo hai aisa? So, let's take this term, x component of this, okay, and leave it like this. So that is your J of R prime dot del prime x minus x prime over some R cube. And this is nothing but some, some vector A dot del prime or some del prime, yes, and some other function scalar, which we can write as del prime dot your F into A minus something, right? I mean, if you expand this, what will you get? You will basically get del F times del dot A and plus del F dot A, right? If you did this. Now we need which one? We need A dot del prime F. We need this. So we need this because we need this thing. So we need this thing. We need this. So I can write this equal to this minus this. Right? Now what is this? This is del prime dot A. What is our A? J. So del prime dot J, I told you that it is 0 because it is a steady current, and del dot J plus del rho del T is 0 is an equation of continuity I taught you a few classes ago. And this has to be 0 because it's a steady current. So the charge density should not change anywhere. And so this is 0, so this becomes 0. So this term we don't need. So we're left with this term. So basically this is your F, this is your A. So this equals this thing that equals what? Del prime dot your F, that is x minus x prime over r cube, and your vector. That's it. We can, so this is just the x component, this goes here, for the y goes here, and the z goes here. Just let me show that this term will give you a 0, because remember, this is going inside the integral, right? This thing will go inside the integral. So this whole thing will go inside the integral. And let me put this term, this piece goes here. So all we have is, in the end, del prime dot x minus x prime over r cube j of r prime. Just for the x component, there will be other y and j and all these terms. Now, we are going to put this thing inside the integral. D tau prime over d tau prime. Now look at this. This is a delta function. So delta function of basically r minus r prime. That's what your this r is. And you know what happens when you take some function of r prime and you do this thing. What will happen? The answer, this will pick the value where delta becomes 0. At r equal to r prime, delta becomes non-zero. Everywhere else it's 0. So this thing will just come out here as f of r, right? So we can put it there, and this will be your j of r, and then we'll be left with just this integral d tau prime del prime dot x minus x prime over r cube j of r prime, and then for the y and z we'll show that this is 0, so others will be similarly 0. Okay, so this integral d tau prime del prime dot x minus x prime over r cube and what? J of r prime. Now this is what? Del dot some function, vector function, over what? A volume. Which volume? The volume that encloses currents, J. Okay? You can take this volume to be bigger than that, and that's okay. Let's say a duster, all the currents are inside this duster. So you can take a volume that perfectly, covers the duster, or any other bigger volume that encloses all the currents. Okay? That doesn't matter, just it has to enclose all the current, that's it. And the theorem, the divergence theorem, to convert volume integral into surface integral, right? So that becomes some surface dA dot this vector, x minus x prime over r cube j of r prime. That's it, right? Del dot this vector function equal to dA dot that vector function. And what is that surface? It is the surface of the volume that you considered. So if you consider this whole volume, then the surface of this volume is that surface. Okay? Now, I told you that you can take a bigger volume, and that does not affect anything, because anyway, outside the smaller volume, the current is 0. So you're just adding zeros, right? Nothing else. So that means I can take really infinitely large volume, then all these currents are inside it. And that means this surface is lying at infinity, right? But then at infinity, your current is 0. You cannot do it here. This argument doesn't fit here because this is a volume integral. Volume integral means you are adding all these points, and there the j is not 0. But now your integral is a surface integral. So this is just the surface. So all the currents you have to consider are at these surfaces. And at that surface your j is 0, because any normal current will end inside, a limited space. So if you go to infinity, there are no currents. And therefore, this j at infinity, so this r prime is the r prime at the surface. And there, this thing goes to 0. And therefore, this term goes to 0 at infinity. And that means this is 0. And equally that will be true for y, z, because the j is common. Here, y minus y prime, z minus z prime. So this is all 0. All we are left with this thing. So we put it here. So just, there was a 4 pi. So 4 pi here. So finally, this thing is del cross B of R becomes mu naught over 4 pi, and from this integral only this thing came. So mu naught J of R. So del cross B is mu naught J. At the position, the current is also at the position where you are calculating the magnetic field. Same point, RR. Okay. There is a little bit of problem when we consider infinite wires of current. A wire going to infinity. Obviously, this current is not 0 at infinity. Okay? So the argument has to be different, but this is unphysical situation. But still, you can show that this is true. And we showed that. Remember in the first class, I just took a loop around it, right? A current, straight wire, and I showed. So this is in general true, but the analysis is slightly different and has to be careful. You don't need it here right now. For any normal physical current, anyway, there are no infinite currents in real life. Okay. Those infinities are just fake. So we really mean is a very long wire, and we are measuring something very close to it. So it seems like infinite wire. Okay, this is it. This is called Ampere's law. In derivative form, in integral form, you can just integrate this. can just integrate this dot dA equal to mu naught J dot dA. So which means just take a surface, some current density like this flowing, okay? So you take an area, so this J dot dA, so this is your area, J is hitting this, J dot dA will be your total current enclosed in that particular area. So this is just the current enclosed by that surface, okay? And this again you can use another theorem, that del cross B dot dA is B dot dL. This should be over the loop. The loop that covers this surface. So if this is your area, surface area, this will be your loop, the end, okay? So, and now we have to of course choose the direction of dl, right, somehow. So you can use right hand thumb rule. If your current is going in this way, let's say, then if thumb is the current, then take the dl direction to be like this. And that's just a convention. So this is your Ampere's law in integral form. This is in differential form. And this is like actually Gauss law of electrostatics, where you had some E dot dA, surface area, the dl was dA, and on this side you had charge enclosed over epsilon naught. So it was E dot dA surface integral equal to charge Q over epsilon naught. It's similar. So like just like your Biot-Savas law is like Coulomb's law of electrostatics. Okay. So if you have electrostatics, that is Coulomb's law, and that corresponds to divergence of electric field, and gives you Gauss law. Here you have magnetostatics, Biot-Savas law. And this will be your Ampere's law or Ampere's circuital law, because it's a loop always you take, so it's a circuit. Okay. All right. Quickly, some applications of this law. I enclosed. If some currents are outside your loop, they don't contribute. We are not going to consider them. Okay. This is very useful and powerful only in situation where there is a symmetry, otherwise useless. For example, consider Gauss law. So you had a point charge, just Q, sitting somewhere, and somebody asked like, what is the electric field here at a point r away? There Gauss law was useful. Why? Because you can draw a sphere with your point to be on the surface, and this is a symmetric situation because the magnitude of electric field will be same here, 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 all these points. And that means if you did E dot dA, you know, magnitude of E, magnitude of dA, you could just take out the magnitude outside, because on the whole surface that you are integrating, E is constant. So you could take it outside, right? And then you can use this, and integration of dA is of course simple, right? The surface area. And that was your equal to Q over epsilon naught, Q enclosed. Nice, and you get E. But you put another charge and you can't use it anymore. There are two charges, let's say, okay, Q1 and Q2, with slight separation between them, and you can't use Gauss law anymore. Of course, Gauss law is true. Gauss law is always true. So if you had a surface, then yes, E dot dA on this surface is still Q1 plus Q2 by epsilon naught. That is true. But it's useless, because now you cannot take E outside, right? Because E is something here it's different. You cannot, if you take a sphere, then the value of E here, magnitude, will be different here, right? It's not symmetric. This surface is not symmetric. If you could draw a surface that is like really symmetric, you can in principle. It will be something like this. Okay, maybe. If you could draw, then E would be same in all points, and then you could use this. But that surface, calculating the area is again complicated. So the point is, it's useful only when you have nice symmetric surfaces. For example, infinite charge density, then you could draw a cylinder. So your electric field was constant in the surface of the cylinder. Or you could have a infinite sheet of charge, and then on every point on top of it, the electric field is going to be the same, because from wherever you look, you have a constant view, right? If you move somewhere else, it's still infinite in this direction, infinite in that, infinite in this. So it's still the same view. So electric field is same everywhere if your distance is same. Turns out that it does not even depend on the distance, because if you go further away, so a distance increases, but at the same time the area of view increases. So more charge is on the view now. So charge increases. Anyway, so this is also again a symmetric situation. You can use Gauss law. Similarly, Ampere circular law is useful when this loop is symmetric about your current. For example, let's take an infinite wire, current wire, I. Right? Take the circle around it, and that will have the same magnetic field in each point, right? Because same distance, let's say the distance is r, then you can use B dot dl equal to mu naught I enclosed is just I in this loop. So taking the magnitude, B and dl has the same direction, right? L is directed in this way, B is also directed in this way, you know this from, so they are same direction. So, and B is constant, so we can take the B outside and take the dl equal to mu naught I. So we have magnitude of B equal to mu naught I by this, and this is what just the circumference of this. So 2 pi r. And we know the direction, this phi direction. So we got the magnetic field of an infinite wire quickly. Earlier we had to do what? Some integration over dl, remember? From minus infinity to plus infinity and all these things. But this is quick, just because there was a symmetry. Let's do another problem. We have infinite sheet of current. So the currents are flowing like this, extended up to infinity, extended up to infinity, all going in, let's say, coming in this direction. Okay? So when you have a current going in a surface, we talk about surface current density. How many currents passing a particular unit length? That's your surface density. Take a length, how many are going in this direction? And we can use once again, so B, okay, what surface are you going to take? What loop are you going to take so that it will be symmetrical? Cylindrical like enekwa hobo. Cylinder jodi ami loi etia e point, let's say current bilak enekwa ase. They're coming out from the surface like this. Okay? If I take a cylinder, A point aru A point belag distance symmetry nai. You can take, just like the electric field case, a loop like this. Now, of course, this piece is not symmetric, but these two are. And the good thing is that this piece will not have any contribution. Yes, so because, your B will be perpendicular to this length. Because how will be the B? Take one of them, it will be like this. For the another one, like this. Another one, like this. So they all will add up. If they're really close, they will give a magnetic field like this. Right? Eta wire lole enekwa hobo. Next wire karone enekwa. So middle etu enekwa ise etu enekwa. So middle cancel hobo. Cancel hoi. Actually oporot flat eta magnetic field enekwa jabo. So it will be a magnetic field like this, in this direction upward, and beneath the surface magnetic field will have a direction like this. So this part doesn't contribute dl. So current a directional, let's take dl like this. So dl this way, dl this way, dl this way. So these two don't contribute. Okay? So if I expand B dot dl, there are terms like, let's call this up, this is down, this is left, and this is right. So there will be B up dot dl up. Okay? So B left dot dl left plus B down dot dl down plus B right dot dl right equal to my current enclosed. How much current is there? So you have to just count how many are there. So the K dot dl will be really the current. This K is how many currents per unit length. So you multiply that by the length, you get the current enclosed. Okay? And so how many really? This length, only this length. So if the length of this piece is L, then it is just what? K dot L. So let's take this length to be L and this to be A. So this current really is just how many inside this length. So current will be K times L. So mu naught KL. This is your current enclosed. Right? Now this up and down, fine. These things will be 0, left and right. Okay? And in any way, B is whatever here, the magnitude here and magnitude here will be the same. Right? Same distance. The direction is different, but magnitude is same. And look, DL and B has the same direction here. Again, B and DL has the same direction even here. Okay? And the magnitude is same. So basically this and this are the same thing as a product if you forget about the direction. Also, I mean same direction. So B dot dl, they're same. So I can just write 2B dl, right? Considering B as up and down the same thing equal to, so let's call this BU magnitude equal to B down magnitude equal to just B. Okay, just B. Then the dl equal to what? KL. KL. And so finally I can just take B outside because it's constant everywhere. So I can take it outside the integral. I have magnitude of B, and integration of dl is what? Just L. So twice L equal to mu naught. Oh, there is a mu naught. Mu naught K L. So L jabo. Magnitude of B will be mu naught K by 2. Ask any kitabot answer. এটা ধৰিছে মানে এটা ধৰিলে নহ'ব ইয়াত চাৰিটা মেইনলি আছে 2 3 4 দুটা 0 ৰাইট b dot dl equal to mu naught ni n মানে কি ইয়াত ধৰিছে just n number of wire ধৰিছে মই ধৰিছো actually এটা continuous current charge density to convert কৰি দিলে হ'ল পিছত just what will be k তোমার length or n divided by length হৈ যাব k okay usually the current or density is convert কৰি দিলে হৈ যাব so this is my mu naught k by 2 this is my magnitude and direction we know right upward it will be minus x direction downward depending on current কোন পিনে গৈ আছে current এই পিনে আহিলে ওপৰত এনেকুৱা হ'ব তলত এনেকুৱা so basically we can write b equal to mu naught by 2 k x plus hobo if down right aru minus mu naught by 2 k hobo x cap jodi up hoy current jodi enekwa flow kore then so that's it easily we did it using Biot-Savart's law it will be difficult. Let's do at least another example. A solenoid, okay, infinite solenoid. Let's take the current to be like this, like this, or if I take, let's take this way, or this way, yeah, great. The current this way. So if current this way, okay, we'll talk about this, which direction. Eta important bostu ase here, you have to consider, is that you have to take the solenoid to be really tight, okay? They're tight like this, one wire after another. Otherwise there will be a complication. Otherwise there is a slight angle in this direction, like if you increase the distance then the springs are really like, and then you cannot approximate each of them as a circle. You cannot. The angle will increase, it will at some point becomes like this, but if you take them very tight you can take each turn as a circle. The angle in this upward direction will be negligible, and that is important. Otherwise this whole analysis and result will not be valid. So it's a tight, very tight solenoid, okay? And there are n turns per unit length. Per unit length. N turns per unit length. So in a unit length there are n number of turns. Okay. So what is the magnetic field inside? What is outside? This is the question. And first of all, you can guess the direction of the magnetic field. Once again, just like the wire, you know, take one of this piece, apply your thumb rule this way, for the other one this way, for the other one this way. You will see that only it's going upward. Okay. Outside also going maybe downward, but we'll see. We'll see. At least inside for sure. Outside, another thing is if we go far enough, and this is a long enough solenoid, but if you go really far, then magnetic field should be 0, right? It's a practical requirement. Whatever your solenoid is, you can go very close to it and consider this as a very long solenoid, which it is. But if you go far enough, the magnetic field outside should be 0. This is one assumption we must have. Okay, then let's start. What can we take as a symmetric surface loop? Just like the this infinite sheet, it's exactly same. Imagine if you take a box here, then you have this current going, and at this point, at this surface point, so they're going like this, going like this. So this point looks like an infinite sheet of currents. So you can take a loop here. So that's what I'm doing. Okay. So at this point, this current is going through the surface perpendicularly. Okay. There is no angle. So if this is like this, the loop stands perfectly perpendicular to the current that is going through it. Okay. So this will give us the magnetic field here, right? This will give us magnetic field here. This will give us magnetic field here. Okay. And we'll consider another just outside. Another loop for some reason. So let's first start with this one. Outside. This is still asymmetric. Just there is no current inside. Right? But it is still, I mean, this line, look at this line. This line will have, for the whole length, B will be constant here. At least this is true. So whatever the magnetic field here is, it will be same throughout this length. Is this true or not? Symmetrically. Iyat eta iyat beshi hobo niki? Kyo beshi hobo? Mane this pointer or this pointer majote ekko difference to nai. It is parallel to this long solenoid. So symmetry argument says that iyat jiman hobo tat maybe tat belek hobo. That's a different issue. But at least on this line, it will be same. Okay. So a distance to center pora, let's say A, or a distance to center pora B. Okay. Aru a contribution a dutar karone 0 hobo. On magnetic field and equa directed hobo. So we can forget about them. Okay. Just let's say here here we have B. A, let's say at A, B at A distance, and for this we have B at some B distance. Okay. So let's apply Ampere's law. It will be BA at A dot this DL. Okay. And minus hobo hitu current. Let's see. তোমার লুপ যদি let's say loop এনেকুৱা হলে B direction, let's say loopৰ direction এটো লৈছো মই, then ইয়াত যেটো direction আছে তাত এটো opposite হ'ব, কিন্তু B ৰ direction তো same হ'ব, right? So B dot DL ইয়াত কিমান হ'ব, এটা যিকোনো মানে whatever it is. For the other one, it will be B at B dot DL minus hobo. Eto clear niki? Karon L or direction change hoise. B iyat eta beleg value hobo. Iba kom hobo. Iyat beshi hobo. But direction is same. ইয়াৰ পৰা ইয়াত গ'লে কিয় বেলেগ হ'ব দেৰ ইজ ন' লজিক কাৰণ ইয়াত যদি এই ডিৰেকশ্যনত মেগনেটিক ফিল্ড তাত যদি এনেকুৱা হয় দেন ইয়াত কিমান হ'ব কেনেকুৱা হ'ব চিমেট্ৰি চেজ যে তোমাৰ কেনেকুৱা হ'ব লেটছ এ কাৰেণ্ট যদি এনেকুৱা ফ্ল' কৰে ভিতৰত কাৰেণ্ট এনেকুৱা কৰিলে ভিতৰত আপৱাৰ্ড যাব বাহিৰত ৰাউণ্ড কেনেকুৱা হৈছে এনেকুৱা চ' দ্য বি শুড বি দিছ ৱে right this way so yat let's take this like this and this then and this so yat b dot dl plus hole tar karone minus hobo right are equal to mu naught current enclosed ইয়ার কারণে current enclosed কিমান লুপৰ ভিতৰত কিমান কারেন্ট আছে no current there are no current so the answer is 0 that means aru dl or integration to l a to dl or integration same l same length right so this equal to this aru dl or integration hoy l hoy jabo dl or integration hoy l hoy jabo l cancel tar mane whatever ba must be equal to bb so this tells us Ampere's law whatever be the value of magnetic field here should be equal to the magnetic field there. Now, I can take this loop to be very big. Okay? Durot loi goi ami complete korim ta. Then this thing is valid. BA equal to BB. But we said that bahut dur gole magnetic field 0 hobo infinity. So BB for sure has to be 0. And this tells me that BA has to be BB. So BA is 0 hobo lagibo. That means outside magnetic field 0 hobo lagibo. So outside magnetic field is completely 0. Okay? So and this will help us in determining this loop. Now we take a loop that has half inside and half outside. We have just proven that outside magnetic field is 0. So this B dot dl here, we don't care. It's B is 0 anyway. And these two we don't care again. These are perpendicular. So only thing is just hold this B dot dl turns out to be just B inside, right? dl inside. That's it. And mu naught into current enclosed. বুঝি পাইছা না কম পাইছা না perfectly okay right বাহিৰত 0 ইয়াত contribute নকৰে just this one so inside again this will be constant because of symmetry whatever here so we can take it outside the integral and that becomes B inside magnitude and dl হৈ যাব some l length jiman ami lom so l equal to mu naught I enclosed kiman I said that there are n turns per unit length eta turnot I current aru eta turnot I current so n ta turnot ni current aru length di multiply kori dile hoi jabo tomar kiman current আছে কারণ n turns per unit length etu l di multiply korile kiman ase ahibo so I enclosed becomes n l I right ni is the current per unit length into length gives you the current in this loop etu increase hole current to increase of obviously right so l go so we have B inside equal to mu naught n I. Key direction hobo z direction along the axis. So that is the magnetic field due to a solenoid. এই ইউনিটত লাস্ট এটাই আছে আৰু আজিৰ কাৰণে নকৰো তোমালোকে এটো কৰিবা actually yeah you do it it's just one line torusৰ কাৰণে torus is just এটা solenoid লৈ এনেকা বন্ধ কৰি দিলে that is a torus so the solenoid আছে স্প্ৰিঙৰ নিচিনা এটো এনেকা ধৰি বেন্ড কৰি এটা সার্কেল কৰি জয়েন্ট লগাই দিলে that will become a torus. Okay? It's like a donut. So donutৰ কাৰণে similarly তোমাৰ এনেকুৱা similar logic এ বাহিৰত 0 হ'ব actually. Okay? So তোমাৰ যেটো ল'ব লাগিব similar logic এ নহয় আৰু easy logic এ বাহিৰত 0 হ'ব. Just take the loop carefully. And then আহিব actually ভিতৰত এটা field আছে বাহিৰত 0 থাকিব